In the middle of dynamic world development, it can't be denied that data has important and vital roles. Various fields of life, such as economy, health, education, and others, need data as a basis for planning and policy making. However, in reality, data incompatibility between one agency to another is still being often faced with a problem. Therefore, validated data is needed. Official statistics produced, collated, and disseminated by National Statistical Office are almost nationally representative because they are obtained from complete censuses or large-scale national sample surveys. On the other hand, the modernity of technology supports the production and dissemination of data that can be done very easily, anywhere, anytime, and by anyone. Big data, a data source besides census and survey, also have an important role at this time. By combining survey data with available administrative data in big data, NSO can save the cost of data collection and processing and reduce the respondent's burden. The new idea of using multi-source statistics brings new problems. One of them is the complexity in multi-source statistics production, which is combined from various high-variation sources. Although various research has been done continuously, there is no indication which method could be applied in a particular situation arising in practice. The increment of volume and variations in data types and sources increase computing power and improve data science methods to change society in fundamental ways. What is the role of data science and official statistics in this disruption era and its relation to developing new statistics and using modern data sources?
Assalamualaikum warahmatullahi wabarakatuh. May peace be upon you. Good afternoon, Your Excellency, the Chief of Statistics Indonesia, Dr. Margo Yuwono, the invited speakers, Professor John Bernard Chattelang, Dr. Alexander Kowari, Associate Professor Julie, PhD, and Dr. Walter J. Rademach. Your Excellency, the First Echelon of Statistics Indonesia, Your Excellency, the Second Echelon of Statistics Indonesia, the Honorable Director of Polytechnic Statistica STIS, Dr. Ermi Asoti Ahmad,
the Honorable Vice Directors of Polytechnic Statistica STIS, the delegation of Ikatan Statistisi Indonesia, the delegation of Forum Pendidikan Tinggi Statistika, distinguished guests, participants, ladies and gentlemen. We are delighted to welcome you again to the first International Conference on Data Science and Official Statistics 2021. Jakarta, 14 November 2021.
First of all, let us introduce ourselves. My name is Iwayan Gede Angga Krismawan and my partner Nabila Anindita. Today, we will be hosting you for the second day of the conference. Our deepest gratitude and praises are for God, the Almighty and the Most Merciful, for the blessings He has given to us, so we can attend and participate in this event today without any obstacles.
Ladies and gentlemen, let me also extend the warmest welcome again to the first International Conference on Data Science and Official Statistics 2021, organized by Polytechnic Statistika SIS in collaboration with Forum Pendidikan Tinggi Statistika and Ikatan Statistisi Indonesia. The conference brings together academia, researchers, business, and practitioners responsible for strengthening the contributions of data science and official statistics to society in the disruption era. This conference is conducted virtually as the condition of the COVID-19 pandemic does not allow it to be held offline.
Ladies and gentlemen, without further ado, let's get straight into our main session today, the plenary presentations of the first International Conference on Data Science and Official Statistics, Day 2. Before we begin with the presentations, let's introduce our moderator today, Mrs. Nuka Widawati Kusumoprojo, PhD. She is a lecturer in Polytechnic Statistica SAS and holds a PhD in economics from Université Paris en Panthéon-Sorbonne in France and Universidad Nova de Lisboa, Portugal. Mrs. Nuka, please take the floor.
Thank you very much, Angga, for introducing myself. The speakers, Professor Zhang Chatlang, Dr. Alexander Pai, Associate Professor Wu Juli, and Dr. Walter J. Radermacher, Director of Polytechnic Statistica STIM, Math, distinguished guests, lecturers, students, ladies and gentlemen. Good afternoon. Let me introduce myself once again. I am Nuka, and I'm serving as moderator for this plenary session. In this plenary session, we shall have an outstanding presentation from our prominent speakers, whom I believe shall enrich our insights and knowledge regarding the theme of the ICDSOS, stating the contribution of data science and official statistics to the society in the era. Before we continue, I would like to mention the agenda of this session. It will start with the invited speakers, around 25 minutes each, then follow with the question and answer session. The audience may write question in the provided link by mentioning the questions. Don't forget to write your name and affiliation. In today's discussion, we have the first speaker is Professor Zhang Bernard Chatlang from Université Paris en Panthéon-Sorbonne, France. The second one is Dr. Alexander Pai from Statistics Austria. The third one is Associate Professor Wu Juli, PhD from Seoul National University, South Korea. And the fourth one is Dr. Walter J. Radermacher, President of Federation of European National Statistical Societies, FENSTATS, and former Director General of Eurostat. Before the presentation begins, allow me to introduce the Our first presenter is Professor Zhang Bernard Chatlang, is Professor of Economics and Finance at Université Paris en Panthéon-Sorbonne and Professor at Paris School of Economics, and also Co-Director of the European Research Group, GDRE, on Money, Bank and Finance, Vice Scholar at CEPREMA, Paris. He got his PhD from European Doctoral Program, EDP, in Quantitative Economics from École d'études en sciences sociales, Paris, Université Catholique de Louvain, Belgium, and London School of Economics, United Kingdom. Master Economics, Econometrics and Statistics, and from École Nationale de la Statistique et de l'Administration Économique, Paris. His field of research are money, banking and finance, monetary policy, finance, development and growth, theory and applied econometrics, many article panel data, a pretest estimate error policy in the new model with public data. The complete list of published articles can be found in websites. Incident event, for example, will deliver a presentation entitled "Pool in order to unpool" and other tips using panel data econometrics. Around 25 minutes. Ladies and gentlemen, please join me in welcoming Professor Zhang Bernatchatlang. Professor, the time is yours.
Okay, so thanks a lot. So can you hear me properly?
Yes, Professor.
Okay, thanks a lot. So it's a great honor for me to be hosted by your conference by Statistics in Indonesia. So really, I do emphasize this. I'm very pleased to do this. So myself, as Nuke mentioned it, so I'm not a pure statistician, but originally I was trained by the School of Statistics in France, which depends from the National Bureau of Statistics, which itself was founded many years ago by members of École Polytechnique. So that's another polytechnic word like the one of you Statistical Institute. So as well, I came in your very, very beautiful country many years ago, and I still have on the shelves some record from that may look very much out of date for you. So from music from Indonesia or whatever. So now let me share my screen. Okay. So can you see my screen? I hope it's okay.
Yes, it's already appeared, Professor.
Okay, so have a look at the papers presented at the conference. Some are pretty technical, many use applied econometrics. And so although I'm not a statistician from a statistical bureau or statistical office, so I will try to give a presentation which is moderately technical and relatively practical in the sense that myself, I'm not a theoretician of econometrics, I'm a practitioner. And my theme is about what I do very often, and since 20 years, many of us use the data where we pull time series of different individuals, and then we use some of these so-called panel data estimator. That's it. So, and the main theme of the talk is to say, well, we pull, but in fact, at the end, the main interest is when we pull, we look at differences across some groups of individuals. Okay. So my periods are as follows. So first we pull, then we unpull, and the synthesis, and we pull in order to unpull. So that's a bit strange, but I will try to be more precise. So when we pull individuals, in fact, it's not only stacking the time series of two individuals. We also assume that they would have the same correlation. That is, that the slope of an individual, of an effect on one variable of an individual to another variable, the covariance, would be the same for the second individual. So that's a strong restriction. And from this restriction, we gain a lot in one dimension, but perhaps artificially. That is, we have an increased accuracy of parameter estimates. But on the other hand, we have a decreased accuracy of the forecast of the dependent variable due to the common slope restriction, which may not be something which is actually into the data. That is, for the first individual, its sensitivity of the variable X and the variable Y may be different from the second individual. And then we have indeed this classical Cho test invented by the Chinese researcher Gregory Cho in 1960. Okay, so what do we do when we pool? So we stack time series cross-section, and we assume at least for two individuals, they would have the same parameter, the same slopes as we say in regression, although we would allow some different intercepts. So you see, so either we pull time series of with T observation from an individual, so sometimes and most often they are unbalanced, that is, we do not have the same number of periods for each individual, or conversely, we pull cross-section during T period, and sometimes we do not have the same individuals in each cross-section. So sometimes we could have also more indices than just individual and time, but to simplify matters, I just consider these double indices. So we pull time series for with index T for time and with index I for individual. So the samples are different depending on what you're handling. So if you have daily data, then you have large T. If you have annual data, you would have very often small t. And if you look at country level or regional level, so I know that in Indonesia, you have very good regional statistics. So from a couple of PhD students from Indonesia who have submitted PhDs in my university. And so then you could have, say, 120 region or whatever. And then you have surveys, individual surveys, but these surveys need to be repeated over time with the same individuals to be panel data, where you have very large N. So the discrepancy between the magnitude of T and the magnitude of N leads to different outcomes. Okay, so the smallest indeed would be two individuals over two periods. That's one example. And you see what we do usually, and some of you, many of you, at least in the papers I've seen from the list of the conference, or some of you are using panel data. And what we do is, for the time series, which are two different columns, so we put one column below the column of the second individual, below the column of the first time series of the first individual, to have a single variable, which is what we call stack data, where we pull time series. Okay, so we have some transformation that we often use, so the average over time for each individual, the between transformation, and the within group variation, the within variation across time. Okay. And here, if I have two variables which are stacked, then I could consider with two individuals, number one, number two, then I could consider different intercepts, so that beta 1 and beta 2, and different slopes, beta 1x, beta 2x. And then I could consider this, I will not develop, that I have disturbances into the regression, so measurement errors, which some of them may be specific to an individual repeated over time, and some of them may be specific to time, and some of the disturbances may be related to individual and time. So the focus of panel data is, the first step is to stack. The second step is to assume at least that the slopes are identical for at least a group of individuals, while allowing, that's what we call the fixed effect models, different intercepts. Okay. So we can pool. So that's I will take an example. So I sent this note to Nuke, so that could be spread to the conferences. So it's a note from what I'm teaching on panel data. When very often, so we use some classic samples which are repeated in various textbooks. are really low, even if we pick only 3 explanatory variables. Okay, and then we have something magical when we pool time series. Then for say 20 countries, or say in the case of Indonesia, 120 regions, this regional data, then we expand a lot the degrees of freedom. Okay, so that's the first big advantage. That's we have much more information. Now, the other thing that we have a model which tries to explain gasoline consumption divided by the number of cars as a function of its macro data, GDP per head, so that's the income effect. Then we have a relative price effect, so that's just demand. Then we have the joint consumption with gasoline depends on the number of cars, the car's equipment. And that's where comes an issue which matters, that in fact there's endogeneity of cars. So cars depends on income a lot in those time series. So that means that when we compare time series, when we unpool, that is, we consider each individual time series estimates separately, we have an handicap. We have 2 handicaps. The first is degrees of freedom are baseball. The second is that in this context, there's a high correlation between 2 explanatory variables, which leads to unstable estimates. So that's from the paper, the original paper, and what we noticed that the elasticities for some countries with respect to income are negative, which is not at all what we might expect. And this comes from near multicollinearity. Whereas when we pool, and we have 5 estimators below, when we pool the data for all the time series, we have much more reasonable expected sign and magnitude of elasticities than with time series. And then the T statistics are extremely large, which means that we have a strong precision of the estimate. Whereas you see, with time series, it was with this handicap that I mentioned of near multicollinearity, which is a problem of specification, we have something very disappointing. So we have the impression that it's relatively magical to pool because we gain a lot in the quality of expected results. However, there's a small thing which is a bit surprising. That's the last column, which is the standard error of residuals. The standard error of residual is 0.23 or 0.8, whereas for other estimates, such as the fixed effect, it's on average much larger. So then what we gain is that the parameters are apparently much more reliable. The t-stats are increased a lot. And on the other hand, the root mean square error, the standard error of residual, increased, which is not very good for forecasting the dependent variable. And then we have heterogeneity of the time series. So is that pooling occur for near multicollinearity? It's not very obvious. So let's have a look at the residuals by country. That's pooling with assuming common slope, common intercept, so that's what we call pooled ordinary least square. What we notice that those residuals have a mean which is for all the residuals which is 0, but for each country, the mean of the residuals are very different. As well, the standard error of the residuals for each country are very different. So we have this table name for this, which is heteroskedasticity. That is, the disturbances seems to be different from one group of individuals to another. So that's the main outcome. Now, when we look at the fixed effect model, now the residuals, they have all the same mean, but the standard error still remain large, and we may have some skewness as well, so that the residual may not be normal. So here in the case of Japan, the mean, which is a small square, is above the median, which signals some skewness, so some non-normality. And now we have the residuals when we unpool. The reason is that we constrain the slopes to be identical, whereas they were not at all identical in the model. So that's a heavy table, but let me pick each of the columns separately. The first line is the within estimator, that is a fixed effect, which is the most common estimator used. And I put a confidence interval to highlight to you how narrow it is. And the prediction is that we should have 19 cases over 20 that our estimates are in between. But when we look at country by country estimates, when we unpool, we notice in bold that there's only in the first column, only 4 observations out of 20 which are into the confidence interval. Okay, so the same applies for the next 2 columns for the estimate. So we have something which is very precisely estimated as an effect because of a low standard error, because of very large decrease of freedom, but we have in time series when we unpool very unreliable, seemingly, outcomes. Now, the first column is the intercept. The intercept in time series tends to be extremely different from the intercept with fixed effect. And the column just beside is the increase. The largest increase is for Sweden. So with time series, it's minus 0.2, 0.89, and we need to add 6 units to have the fixed effect, which is obtained using the intercept from fixed effect. Okay, so that's a big change, and this is related to the constraint that we set on the slope to be the same, whereas they were not willing to be the same. So there's a report of this which goes into the residuals and which goes onto the intercept, which is, so to say, when we biased the intercept and we biased the standard errors, the root mean square error. Now, the last column, the column just beside, it's the standard error of, say, the residuals, for example, of Japan, divided by the standard error when we did not restrict the slope to be the same, that is the standard error obtained with the time series. And it just multiplied to the extreme case by 9. Okay, so that's, and the last column is NFS. So I will just highlight in the next slide. So what I commented from this table, that is, first, we look at the parameters and the confidence interval. Does it fit with what we observe country by country? And it seems to be extremely precise with respect to what we obtain with time series. Okay, so that's what I mentioned, that is this very narrow confidence interval. And then country by country, only a few of the countries are within this interval. Intercept estimates are very different. So I gave the formula in the note. In fact, you have a theoretical formula which is not written in textbooks that just explains how you have this bias. This bias is a difference between the common slope estimate. So it's the difference of the country estimate minus the common slope estimate, weighted by the average value over time for this individual of each explanatory variable. So for Sweden, we have difference of parameters times the mean of, say, the log of output per head, which is minus 7.8, plus difference of the second variable times the mean for Sweden of the log of price of gasoline divided by the price of all the goods, and the last term, when you have the mean for Sweden, of the logarithm of the car equipment per habitant. Okay, so this is normal, and that's a signal that, in fact, what we call fixed effect, that is intercept, which are specific to a country, they are biased by adding the sum of these terms, that is the difference of the parameters of time series without constraint, without restriction, and the parameter obtained with the common slope. Okay. And then at the end of the day, the fixed effects, the intercept that we found with the fixed effect models, they are not reliable for diagnosis. We should not sort or do an interpretation of, say, the country with the largest intercept is, for example, the US, because they are the world leaders at the time in GDP. But in fact, it's mostly driven by a constraint on slopes that the time series would not accept for minimizing least square. Okay. Now the sum of square, why does it increase? It's a variation of this. That is, this times the difference of parameters times the difference of the observation of, say, gasoline per of output per head for Sweden at a given year, minus the average over time for Sweden, if I is Sweden, for this variable. Okay, so that goes into the disturbances because we restricted the parameters to be of the slope to be not what they were willing to do. This goes into first the intercept, one component, and the second component, the deviation from the mean, goes into the residuals. And then we have a formula which looks a bit heavy, but that the variance of the sum of the difference of the parameter that it would be without restriction, the parameter that it is with restriction, times the deviation, what we call the within deviation from Sweden for each variable. So this means in the middle we have a covariance of this deviation from the variable in the sample. And then we have the difference of parameters that we've seen already for the bias in the fixed effect. Okay. And then we return to have this difference of standard errors. Okay, so that's this. How to explain? There's two ways. So I just first computed from the residual of the standard errors and did the ratio, but afterwards I check the theoretical formula, which is on my own. So I just applied this, that it corresponds to the data. Okay. Now F-test. So what you see, we have difference of standard errors. So that's what appears on this slide at the bottom. And we have what we call F-test, which are show test also, or Fisher test of checking a restriction. So we pick the residuals on the top here in the case of restriction. That is when we constrain the slope to be the same, minus the residual if we do not restrict the slopes to be the same. That is in the case of time series estimates. We divide by the time series estimate and we take into account the number of restrictions, and which are k, which is k slopes are identical for k variables, that is k equal to 3, and that's it. Okay, and which are k. Yeah, and so k is the number of explanatory variables, t is time, and n is the number of individual. Okay, and then we have this is an individual F-test for a given country. It's very large as a statistic for Japan, for example, because it just correlated. It's just a function of the difference of standard errors with restriction and without restriction. And you have the pool global test, which was in fact done originally by Ronald Fisher. And then, okay. So what's the outcome of this test? In fact, they reject the hypothesis that the slopes are the same for the individual, say in the case of Japan, or for the global, all the countries together. Okay, so that's the story of the shape. So the larger is the statistic, the smaller will be the associated probability that we could accept the null hypothesis. So that's from the textbook. So I found the same result for the global. And now that's an explanation by Di Baltari. On the very original paper, I think at the time people were not doing panel data, so he's defending the use of panel data. It's not at all as it is now, where now a lot of people are using panel data. And what we observe that the Fisher test is so large that the corresponding probability is has a probability to happen to be infinitesimal. Okay. Nonetheless, it says, well, the resulting power of the test statistics will be poor or whatever. So we do not need to pay attention to this heterogeneity. So which is, I think, a mistake. So what we could do.
I'm sorry, Professor, but 3 more minutes. Thank you.
Perfect. I'm in time. So what could we do in this case? So we could change the specification. We could check if we can pool subgroups, or else, in some other cases, it may turn that regions are very different, and then it's better to just to keep time series estimates. Okay. And as a nutshell, to give you one of the answers to this issue was, in fact, for example, so what I tried was just to change the specification to remove the multicollinearity and to divide by number of inhabitants the dependent variable. And then I turned to have something relatively exceptional, that is there was no longer any multicollinearity. The outcome from the pooled and the unpooled were very close. And in addition, what we call the between regression was also close. So you see, the answers are not exactly what you think. Sometimes it may be changing the specification could improve your result, and then you may have an answer to the issue that is, in this case, it turns to be good to pool in a sense, because when we unpool, it was relatively the same. So that's my main message, and I will just go on with this last slide. So what we very often do in panel data is to interact terms with the variables, and there's a good reason why it always works, because in fact, else we would assume that the slopes are always the same, and when we add this dummy variable for groups that we interact, we in fact allow slopes to be different, and in this case, in fact, very often we are winning in terms of exploring the data, because in fact we unpool into various groups to check for results. And the final element is the typical case where we have an interest to unpool is the case of what we call different inferences. So we have a crisis, and we have a fragile group of individuals or firms or banks, and some more to some effects after the crisis than others, even though they would both of them change. So that's, you see, the typical interest of data, panel data pooling is in fact to pool together persons or individuals of a different period, and then to add dummies that would correspond to different period events and different groups of individuals. So that's my main message, and thank you a lot for your attention. So
Thank you very much. Thank you very much, Professor. It is a fascinating topic with a crystal clear explanation from you. I'm sure that the audience has more questions in their mind related to your presentation. Again, the audience may write their questions in the provided link. So our next presenter is Dr. Alexander Kuarik. From data manipulation, data analysis, exploration, train support, theory and survey methodology, and scientific research. Many of his works are published in the journal, and many of his works are SRA such as survey standard error estimation for cumulative estimates and their difference in panel designs. Today, Dr. Alexander Parik will present a presentation entitled DevOps in the statistical production process with R tools. To Mr. Parik, the floor is yours.
Thank you very much. It's an honor for me to be here. Can you just confirm that you are here? Do you hear me all right and that you see the presentation?
Yes, it's already appeared.
Okay, perfect. Thank you for the nice introduction. I have a maybe a bit strange title, so DevOps in the statistical production process, with a subtitle of Modern Official Statistics and R for Official Statistics. So it's also kind of new because I'm a methodologist, so normally I talk about the introduction of new methods, the development of new methods, or how we implement a method in R package. So that's is my standard set of talks. But today I want to present more like a bird view on computing in the statistical office and how it actually should be or will be set up in the future, or in what direction we are going. So it's a vision for building and modernizing the statistical information system, and what factors are important there. So I will talk about computing in the statistical office in general, the statistical production process, and at the end a bit about R. So computing in the statistical office. I took this picture, so that the left picture with the circles, from a recent publication by Mark van der Loo from CDS, from the Statistical Office of the Netherlands. The publication is called Computing in the Statistical Office, and it's showing the different skills or different tools actually needed to be able to do all the computation in statistical office. So if you start at the top left, you have computational statistics. So that's something you would expect there. So you have all kind of optimization, linear algebra, MCMC, maybe parallel computing is also a bit there. Then you have methods that are still computational statistics, but a bit more specialized on official statistics. So statistical disclosure control, for example, or error location. You have advanced computing skills, so parallel computing, distributed computing, functional programming, object-oriented programming. So things you need to actually implement methods in a proper way. Statistical computing as a whole is, of course, the whole bubble. That's the next point. But then you have data management, because you actually have to access data. So thing is, of course, SQL, but also more abstract things like metadata, schemes, information model, how you set up databases, data structure. All these kind of things are skills that are needed in a statistical office. Then there are skills that are more seen to be coming from the computer science, so software engineering skills. So you need to know how to use an IDE. You need to know how you use version control. You have to develop packages. You have to test them. To disseminate results, you need skills in the web section, basically, or visualization section. So all kind of interactive visualization, JavaScript, D3.js, and so on. So this picture reminded me of the pictures put up on the right corner as a small picture. So what industry kind of framed or coined for the modern data scientists, what a modern data scientist should be. So he or she should have the skill set in math and statistics, programming and databases, soft skills, visualization, communication. So that's actually kind of similar, not framed in a technical setup, but framed as a more generics. So actually, probably what the industry wants as a data scientist in the office is probably similar to what a statistical office needs for in-house expert who does computing in a statistical office. Nowadays, in all job adverts, we of course also write data scientists on the job title, because that's just the cool thing you want to work as. So all these tasks are actually not, of course, done by one person at the office, but it's split up between different persons, different units even. So these tasks are split up between IT, methodologists, and subject matter experts. And of course, these skills are unevenly distributed between these groups. So you have IT development skills, so all this, for example, testing or unit testing is something that's obviously in the curriculum of a software developer, but not necessarily of one of who, like I did, studied mathematics. And if you think about subject matter experts, of course, they can come from various fields, and math skills and IT skills, they are also something to pick up later on. I also want to point out one similarity with something that developed recently called research software engineer. So that's something coming from academia, because also their software is more and more important, and how you are able to build a career basically on software. So the idea there is that it's an own skill set, and also something that's worth researching and worth learning, not just developing new methods, but also implementing these new methods in proper software. So that comes from basically R and Python developers who formed societies here. I put the link on here. So that's computing in the statistical office. Just have to switch because the titles are sometimes missing. So the next thing is how we put that in statistical production. Some of you who come from a statistical office might know this picture. So it's the GSPPM, the General Statistical Business Process Model. It's maintained by the UNEC. You see the link down below. You can look it up later on in more detail. But the general idea is that it's a process model, and you start off a process with specifying needs. Then you design what you want to survey, or you want to collect it, what kind of information you want to collect. Then you build the tools you need. Then you start collecting it. Then you process it. Then you analyze it. Then you disseminate it. And at the end, you evaluate what you just did. And if you look at some of the boxes, some are obviously closely connected to computing in the statistical office, and some are less connected. So maybe the first step, specifying needs, is not very computing intensive, but phases like the build phase, for example, where you actually build tools, that's obviously that you need computing there. Also in collecting nowadays, it's done via web service, for example, or we get big data by web scraping, homepages, etc. So there's computing heavily involved, and of course in process and analyze phase as well. And the disseminate phase is also happening nowadays in a digital manner, so via web page, via web apps, and that's also something computing is involved. So as transition to my next slide, there's another picture on GSPPM, which split up these steps in two phases. So the smaller one in the middle is called the work phase. So that is with a higher frequency, you collect, process, analyze, disseminate. And then probably with a lower frequency, you evaluate, specify needs, design new information you need, and then build the new tools. And if you keep this picture of two circles that are interconnected in mind, and I go to the next picture. So the most common picture you see when you type DevOps into Google. It's actually looking quite similar, but it's not, the circles are not within, but they are next to each other, but they are still connected. So DevOps is a set of practices that combine software development and IT operations, and it aims to shorten system development life cycles and to provide continuous delivery of high quality software. And DevOps has a list or a number of principles, and from my point of view, a lot of the principles could be kind of translated or just applied on a statistical production process in a statistical office, but also more general to like a data processing in any kind of organization, so also in industry. If you have similar quality standards as we have in the statistical office, of course. So a major improvement that can be copied from recent developments there is to build continuous integration and continuous delivery pipelines, also for data processing. So that allows you to react quickly, update data, improve a method, and then run everything quickly. So again, there's one box missing because the deployment at the end is also important. So you kind of have a pipeline you would can think of as in software development, it's something quite common. You push to a repository, and then there's matching happening in the background, and everything is happening. So that's something similar could be set up not just for the code part of your process, so that the actual programs, but also the data part. So if you update the data, the whole process is triggered and it runs through until the deployment phase where you disseminate results, for example. And all kind of data science, machine learning, and statistical methods can be implemented in this process. Also, just as a keyword, also infrastructure, if you think about virtualization, can be implemented in such a process. Of course, what cannot be implemented in such a process is the actual collection of data. If you think about surveys and respondents should respond, that's not something you would have to wait for that to come in, and you can not just run through the process. In software development, testing plays a crucial part, and testing should be included in the organization. Testing in terms of unit testing or software components you use in the process that are, of course, developed especially for this process, but also more general or more data logic testing, so plausibility checks for the data should be included. That you can see parallels to automated data editing there. So data editing checks could be checked by this pipeline I talked already about in one of these processing steps. And it would be good to compute quality controls, quality indicators throughout this statistical production process. And in some special events, I call them here extreme quality events, there should be kind of a trigger, like a pause button automatically pushed by the process, where manual intervention is asked for. There's also a big, strong focus of DevOps on continuous improvement. And one key part there is modularity. And there are also special initiatives on that. So one of that is CISPA, you might have heard of, that is Common Statistical Process Architecture, also something promoted by UNEC. But I would not think about that in a such abstract manner, but just if you set up a process and you use methods, these methods should be kind of encapsulated a little bit, so it's easy enough to swap them against other tools. And another aspect in this part is from DevOps is that you build up integrated teams and kind of end-to-end responsibility to everyone in the team. So in an NSI, this would be statisticians, subject matter experts, and developers in one team, and everyone has end-to-end responsibility for the whole process. Not necessarily meaning, of course, that everybody can like work on every part of the process himself or herself with the same expertise, because that would be quite impossible. Another important thing that's also quite obviously close to the heart of a statistical office is being reproducible, because that also means being transparent. When we, of course, collect data and then process it, it should be in such a way that we can afterwards reproduce and also audit the results reproduced. So making the whole data generation process transparent. This would include things like data versioning, so that you have kind of a raw data set at the beginning, and then you have updated versions throughout the process, and you can actually see from step to step what changed in the data. Probably you will always find some graphical user interfaces for data editing. So in our setup, often data clerks have graphical user interfaces where they look at the most important responses from service, for example, if you think about business statistics, so the biggest companies of a country, for example. And then they see that there are errors, then they would fix them. They may call them and ask for clarification, and then fix that directly in the data. And that should not happen in a way that it's just entered and then a field in the database is overwritten, but it should be done in a reproducible way. One easy step or easy method would be that such a GUI produces code to update a data set, and then this code is applied to the data set. So if you run the whole process again, you can apply this small code that is generated by one data clerk using the graphical user interface again, and you get the same result. So what tools would I see needed for that? Obviously, it's not Excel, which is in the background of the slide, or not just Excel. You need some code-based statistical software product. R, Python are fine. SAS would also work with some workarounds, I guess. You need version control. Nowadays, this basically means Git. Some kind of pipeline tools. Think about GitLab CI, GitHub Actions. In-house in our office, we use Jenkins for that. It's also a pipelining tool. And you have to have some place where you actually store artifacts too. So this could either be the results of such a pipeline could be an R package or a web application, and you need a specific place to store it there. I will go through the next two slides quickly because I don't have too much time left. So I'm going already for tools for this process. And I want to point especially colleagues from national statistical offices to one thing, a community approach to knowledge and to share software. There's a presentation given by Olaf ten Bosch recently, so last year at the Use of R in Official Statistics conference about this list also. So we're using something called an awesome concept there on GitHub to collect tools that are usable in a statistical production process in a statistical office. But if you look at it, it's not limited to a statistical office, but you can also use it in other data producing or institutes. The idea is to have clear and simple criteria when we add the software package. I will show that in the next slide. And in the background, you see the GSBPM, and the green circles show where we actually have tools available there. So the criteria is quite simple. The tool needs to be free and open source and available for download. And the second criteria is that it is used in production in any statistical office, at least in one. So that's okay, and then we put it on the list. And there are all these GitHub things, how you can interact. You can write a pull request if you have a software package you add. And you can like the thing. So we have also social interactions. By the way, this pink sunglasses are the logo of the awesome lists on GitHub. So that's why we also have this pink sunglasses as a logo. So some examples what's on the list, and these examples are 100% biased because that's all our packages that I co-authored with colleagues from Statistics Austria and also Statistics Austria from universities. So the first one is this one process step called edit and impute, and one big part there is of course imputation. And we have developed an R package called VIM, which stands for visualization and imputation of missing values. And you can do all kinds of cool visualizations with missing data and also with imputed data. So the orange parts in these graphs are imputed and the red parts are missing. And the idea is with this visualization to get some kind of idea on the structure and then apply the as good as possible imputation methods. And we have dollar-based imputation like k-nearest neighbor imputation, hot tag imputation, and we have model-based imputations like IRMI, which is for iterative, robust, model-based imputation, and regression imputation, where you can specify different regression models to impute. We have the survey ST package to calculate weights. So that's also a process step that's asked for that exactly. And you can use this R package not just for this process step, but also for steps in the analyze part. So where you compute estimate errors. Because what the package is doing, you can calculate weights with calibration, with iterative proportional fitting, and then you draw bootstrap samples and also calibrate them, and then you can just estimate errors. And there are also some simple visualizations included.
Doctor, I'm sorry, it's 3 minutes left. Thank you.
Okay, that's even more than I anticipated, so that's good. Another example is disclosure control. There's I just mentioned that quickly. So there are a set of at the end 3 packages for statistical disclosure control. One is STC Micro for the disclosure control of microdata. There's also a nice Shiny application where you can look at your data and produce reproducible outputs. That means that we produce code there with the GUI. There's an R package STC table if you have to handle the disclosure control of tables. Here you just have an example of a suppressed table, which is quite easy. You could do that by hand, but it can handle hierarchical tables, data cubes, also with a high dimension. And the last disclosure control package is SynPop, which can be used to generate synthetic data sets based on populations of census files and sample surveys. And you can use that, for example, for public use files. So this brings me already to my last slide. So a quick recap, 2 things. So, or 3 things, one I will add to the list. So think about computing in the statistical office as a very wide field, and which has developed in the last decades, I would say, and it can be seen as something similar what is seen nowadays as data science, I would say, and how we should implement these computing tasks. We can learn from DevOps by optimization, testing, foster continuous improvement, and especially being reproducible. There are many tools readily available for this process, and many of them open source tools. Thank you for your attention. I'm looking forward to getting questions later on.
Thank you very much, Dr. Alexander Kwarik, for the interesting talk. I know that there are already many questions arise from the audience. Please don't hesitate to write it in the provided link. Mr. Kwarik will discuss it in the discussion session later. So, ladies and gentlemen, we will proceed into third presentation. Let's welcome to our third panelist, Associate Professor Wu Julie, PhD. So, Professor Wu Julie, PhD is an associate professor, Department of Public Health Science, Graduate School of Public Health, Seoul National University. He got his PhD in statistics from National University in 2010, continued to postdoctoral program at Department of Medical Epidemiology and from 2010 until 2012. He graduated his BS in Physics at Seoul National University with cum laude honor. His field of interest include causal inference, meta-analysis, medical epidemiological methods, multivariate analysis, mixed models, and non-standard. His academic experience shows that Professor Wu is an expert in this field. He is a lecturer in many institutes, and he taught many subjects, such as at Karolinska Department of Medical Epidemiology and Biostatistics, Indiana University, and National University. He taught many subjects such as biostatistics, multivariate analysis, statistical computing, and topics on generalized linear model. He also teaches in many works or special lectures. He has published more than 100 articles in the journal, and I'm really sorry because in time I could only mention recent books, just except the characteristic of in Rwanda, accepted in global epidemiology. Professor Wu Julie also actively presents his works at many international conferences. His professional activities also so many. For example, as ARB committee member, hospital, an associate editor of Journal of the Korean Society, an associate editor, Journal of Preventive Medicine and Public Health, an associate editor of the Korean Journal of Applied Statistics, an invited reviewer, mathematical reviews, and editorial advisor. He serves as a reviewer such as statistical scientific reports, and many more. Professor Wu Julie awarded many research grants, such as from Karolinska Institute, RV, and Rural Development Administration. He also supervises from the level of graduates, master, and PhD students. Today, Professor Wu Julie will share about the COVID-19 pandemic in Seoul with biostatistics. So, without more ado, please, Professor Wu Julie, the floor is all yours.
Thank you. I will try to share my screen. Can you hear me and see my screen?
Yes, Professor.
Okay, thank you. Thank you for the nice introduction. I'm very honored to give my presentation at ICDSOS 2021, and I appreciate the organizers and local committee members for hosting this international conference, uh, even during this tough COVID-19 pandemic situation. Thank you. Let me start my talk. Today, I'm gonna talk about the reaction to the COVID-19 pandemic in Seoul with biostatistics. Actually, this is my private um, experience with uh, about the collaboration work with government officers in Seoul. Uh, in my talk, I have four subtopics. The first one is about the short-term forecasting for the number of new confirmed and severe cases. And the second one is about the within versus between academic model results. It's about the decomposing of infections into two parts, within infections and between infections. I will talk about the details later. And third subtopic is about predicting the number of new weekly confirmed cases. There is a similarity between the first topic and third topic, but the spatial scale is different. The first one is about the whole scale. The, so, I mean, uh, the first one is about the Seoul, and the third is about the district in Seoul. So spatial scale is different, and the model is different. And the fourth topic is about the SEIR model to assess the non-pharmaceutical interventions in Seoul. So let's study this together. Here is the introduction. And the first confirmed COVID-19 case appeared in Korea on January 12th, 2020. And after that, there have been three big waves. In here, in this figure, it shows the third big wave in Seoul. X-axis is about the date, and y-axis is the number of confirmed cases in Seoul. But to show the pattern more clearly, it shows the moving average result. So the number of new confirmed cases like this one, and then you can see many vertical lines. And here, the red vertical lines correspond to the enhanced social distancing. Okay, and then the blue vertical line is here. It's about the relaxation of social distancing. And this dashed line corresponds to the declaration of annual gatherings. In Seoul, more than 5 people cannot be gathered after that. As I said, this is the collaboration work with the government officers in the health department of Seoul during the COVID-19 pandemic. Actually, our team provides the weekly report, including these figures, numbers. These reports were made to help government officers prepare for the situation of a surge in the number of confirmed cases and identify which areas are at risk in the future. First, I will introduce the data that I used in this collaboration work. Here you can see the map of of Seoul. I found that there is a quite big similarity between Seoul and Jakarta in terms of population and population density. Currently, 0.1 million people live in Seoul, and population density is also very similar between the two cities. And there are 25 districts, which is called BU here. It's a special unit in Seoul. And there are 25 districts. And then these units are basic units in my analysis. Surprisingly, I am presenting this slide here, Yangcheong-gu. This slide shows the data that I used in the collaboration work. Actually, all the data are public, so you even you can download this data from the website maintained by Seoul. This data includes the current status of COVID-19 cases in Seoul, and it includes the number of stores or shops by administrative district. I mean, this number includes the restaurant, gym, and karaoke, etc., etc. I mean, these shops and stores can have potential risks for mass infections, right? So this number is very important in modeling COVID-19 prediction. And the number of vaccinated persons by administrative district is also public. So, and the number of severe cases also available from a public website. I mean, in my presentation, the infected cases is declared to be severe when a COVID-19 patient requires inpatient treatment. And we also use the following mobility data. The mobility data is quite critical in modeling the COVID-19 prediction models. Actually, we construct the origin destination metrics using mobile data. I mean, in this collaboration work, we work with a mobile company, and they provide very detailed mobile information, something like figure 1 here. I mean, the black dot, she just passed the area B. The B is not important in this movement. So after this calculation, we can construct the OD metrics like here. So because this person moved from A to C, as you can see here, this number is added to this cell because the origin place is A and destination place C. And then the follow-up continues, and then some numbers added on other cells, like this one, this one, this one. And then we construct the big origin destination matrix. And then this matrix will be used for modeling COVID-19 prediction. The first issue is about the short-term forecasting for the number of new confirmed cases and severe cases. The aim is to predict a daily number of new confirmed cases for next 7 days, and also to predict the daily number of severe cases for the next 7 days. Here, you can see the two numbers, and then to show the pattern clearly, the result is moving average. The solid line corresponds to the severe cases, and then the dashed line corresponds to the confirmed cases. So you can, before modeling these time series data, you should note that there are some characteristics of this time series data. First one is they are count data. So when we model this time series data, we reflect this property first. And then there's another characteristic is the time series data is really non-stationary. I mean, we cannot assume that, when we model this time series data using time series model, there should be some coefficient in the model, right? But we cannot assume that those coefficients are constant during the entire the COVID-19 pandemic period. This is very natural because the human and society and environment are interacting each other continuously. I mean, the government, the respond to the COVID-19 pandemic situation by implementing a timely policy. By implementing timely non-pharmaceutical interventions such as social distancing or ban on the gatherings. And then the people the humans' behaviors are changed. For example, the mobility reduction will be changed a lot by such non-pharmaceutical interventions. So we cannot assume that the coefficients in the time series model are constant. So we should use only observations for a short period to estimate the parameters in the model. The length of observations to estimate the coefficient in the time series model is also kind of tuning parameters. So we will actually in our application, the length of observations is also determined by cross validation. I'll explain that later with more details. And then another characteristic is here, as you can see here, the increasing trend of confirmed case lead to the increasing trend of severe case, and decreasing trend of confirmed case lead to the decreasing trend of severe case. The confirmed case are precursor for predicting severe cases. This is also natural because some of new confirmed cases can worsen a critical condition. So these characteristics will be reflected using for model for count time series data. And actually, this was developed by Fall and et al. 2006. Here, the count time series YT denotes the number of new confirmed case or the number of severe cases. Its conditional mean is denoted by lambda t, and then here the lambda t, this Ingach PQ model explains how the conditional mean of conditional mean and other covariates. So this is quite natural. So, in some sense, this is quite similar to the concept of Gachi model in finance. The parameter estimation is very straightforward because we will use the we use the maximum likelihood estimation. So once we specify the model, then the parameter estimation can be performed by maximize the likelihood function. This slide explains the model settings for predicting the numbers. This corresponds to the new confirmed case. We have many tuning parameters. How many legs observations should be used in our Ingach model? Actually, this parameter correspond to the P here. How many legged observations should be used in this model? And how many legged conditional means? This corresponds to Q. And we also determine the length of function. And sample size means the length of observation to estimate the coefficient in the Ingach PQ model. So there are several options. And in the covariate, we consider weekend indicator because we know that during the weekend, the number of COVID-19 tests is a little bit reduced, right? So we think that this can be an important covariate. So we consider this in modeling the number of in predicting the number of new confirmed cases. In predicting the number of severe cases, the parameter settings are quite similar, but there are more because, as I told, the number of confirmed case is a precursor for predicting severe case. So we, in addition to weekend indicator, we use moving average of confirmed case and lag confirmed case like this one. So we consider all kinds of combinations of these parameters and covariate, and we choose the best model. The model selection criteria is given like this one. We use the length probability score because we handling the count time series. So this criterion is well known in count time series data literature, and this criterion has good property. Good robust property against the outline observations. So we use this one, and we select the model by minimizing this ranked probability score. Our selected final models are like this one. For the number of U-confirmed case, we select an Ingachi 2.0 model with identity link function, and we only use the 7 days observations parameter. I mean, it really tells the time series data are non-stationary, and the model is we described like this one. For the number of severe cases, we use the best model is Ingachi 1.0 log link function, and 21 days observations are used to estimate the coefficient, and weekend indicator and moving average of the number of U-confirmed cases are used as predictors, like this one. Let's see the result. This is about the result for new confirmed case. Like this one, the the black dots correspond to the actual observations, and then the 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 blue, the prediction interval, are obtained from the bootstrap here. So prediction performance is quite remarkable. Coverage probability of 95% of bootstrap prediction interval has 95%. This is about the result for the number of trivial case, a little bit disappointing than compared to the previous one. The coverage rate of 95% bootstrap prediction interval is 83.7. But as you can see here, there's a two inconsistency between our prediction and the actual values. But for the other period, the prediction performance seems quite acceptable. We think that we also think that why there is such a inconsistency between prediction and actual values, because for the number of severe cases, as I said, we use 21 days rather than 7 days. So within those 21 days, if there is some kind of non-pharmaceutical intervention by government, actually our model cannot reflect that part because we are using 21 days. Even though using 21 days observation gives the best prediction model, there is some inconsistency between the prediction and the actual values. There is a little bit disappointing point. Let's talk. I'm going to talk about the within between model results. This is about the decomposition of the infections. I mean, we consider two effects: within effect and between effect. Within effect means the effect of internal transmission within each district. I mean, maybe going to church or going to temple, something like that. And between effect tells you about the effect of external influx from neighborhood areas. I mean, let's consider a big commercial area and people come to that area to buy something or to enjoy something. Then it's affected by neighborhood area. We decompose the infections into two parts. The model was developed by Hart et al. 2005. The model can be described like this one, and it has three components. The first component is endemic component, and second component is within components, and third component is between component. And within components tells the autoregressive effect within area. I mean, how the previous the count data affects the number of new infections today within that area, right? And how about the between components? It tells how neighborhood at time t minus 1 affect the region of interest at time t through the weighting matrix. And then each area has each their own specific effects, so they can be handled by using random effect models. And weight metrics, there are several options, and the first one is whether they are neighborhood or not. If they are neighborhood, and then that corresponding element becomes 1, otherwise 0. The second option is about the physical distance. So that element corresponds to the inverse of the physical distance between two areas. Third option is about the mobility. So it reflects how many numbers of people move from the region I to region J to region I. I mean, this in the third option, WJI corresponds to the origin destination matrix. Parameter estimation is also quite straightforward because once we specify the model, we can use maximal estimation, and this model can be implemented in the RX surveillance. This slide shows the model settings for implementing the decomposition, and we consider three weight metrics, and we also consider many others, some variations of model. I mean, some model having only intercept, some model having linear time trend, or the quadratic time trend, and something like that. So we compare all these combinations using the previous the scope function.
I'm sorry, Professor. Thank
Yes.
you.
3 minutes. Okay. We found the final model by minimizing the proposed scoring rule. Here, the final model can be described like this one. And the important thing is the third weight function. I mean, the best model choose the mobility information. Here, we consider the difference between within and between effect. And it's defined like this one. And Kangseogu shows the large cumulative result. And it means that Kangseogu has the largest within effect compared to the between effect. And then Gurogu shows the large negative effect. It means the Gurogu has the large between effect compared to the within effect. So Kangseogu and Wanaku, and actually this is the plot of endemic component and two epidemic components. And then as you can see here, the Kangseogu and Wanaku has the dominating within effect. Actually, this is consistent with my common sense because Kangseogu and Wanaku are known as typical residential areas. These two, Gurogu and Dongjaku, and they have the overwhelming the between effect. This is also consistent with our common sense because they have big commercial areas. But it requires more further investigation to have a confirmatory research. Let's go to the third topic, spatial prediction. I mean, this is similar to the first one, but the scale is different. So for each district, we construct a very simple GLM model to predict the number of you confirm the case, but the prediction performance is not satisfactory. So we consider an ensemble approach by combining 8 Poisson models and then using weight function. So the final prediction can be described like this one. Here, the weight function is like this one. And the basic logic behind this weight function is to give larger weight on a good prediction model. So there are several parameters in the weight function. All these parameters are determined by cross validation, and this is our final weighting vector. And you can see here, even for each district, our prediction model shows good performance, and predictive x-axis is predictive value, and y-axis is observed value, and they are they shows quite a high correlation. The last one is SEIR model. Actually our government ask our team to ask us about what if we relax the social distancing at this moment. But we feel very difficult to answer the question because so far we have these empirical models, but we do not know how these models are connected with the effect of non-pharmaceutical interventions. I mean, just imagine that if we relax the social distancing, which parameters are changed? It's very difficult to have such connection. Actually, from the review, we know that most of, to assess the effect of non-pharmaceutical interactions, most of literature employ the mathematical mechanistic model. So we follow that. So the model is the SEIR model. SEIR, they are abbreviation for susceptible, exposed, infected, and recovered, respectively. And they can be described like this one. For more details, maybe you can type SEIR in Google, then you can find more details. But statisticians like to put more randomness in the model, so they change, instead of this deterministic quantity, they replace them with some kind of binomial quantity. Recently, 2021 in Nature, Chang et al. Published one paper, a kind of stochastic SAL model. Actually, the key thing is they use the mobility information in the SEIR model. That's the key. By using the information, they show the good empirical performance in predicting the number of new confirmed cases. The details are like this one, but there are big problems in using that model. In applying that model into Seoul. The problem is depending on the culture, the people, the human behaviors are different across different countries. And another thing is the shops and stores in Seoul. The stores are too crowded in a building. So we cannot employ their model for Seoul. So we developed our own model, and we also use the mobility information, and especially we consider the number of stores or shops that have potential risks for mass infections. That's the key difference. Actually, this shows the empirical performance of our model, and the green line is obtained from our proposed model. If we do not consider the number of shops or the number of stores, then we just have the red or blue lines. They cannot explain the reversal of the trend. This is my last slide. Our findings show some epidemiological implications. Looking at the decomposition, from the second topic, we gain some epidemiological insight to reduce the rapid spread of infectious disease in each region. If you look at the high increase of the new number of new confirmed case, and then if that area is surrounded by the big commercial area, it's better to limit the operating hours of a shop in that commercial area, right? And then social distancing and then on gatherings have different effects on the occurrence of new infections. Actually, this is reflected in our SCR model. And we also consider the vaccination. So we conclude that MPIs should be continued even after vaccination. Maybe many epidemiological researchers agree with this conclusion. Okay, thank you for your attention. Thank you very much.
Thank you very much for your presentation, Professor Ujuli. Now, after 3 talks discussed about panel data econometrics, statistical production process, and biostatistics, we shall continue to our next presenter that will talk about official statistics. For the 4th invited speakers today, we have Dr. Walter J. Demacher. He was a Director General of Eurostat and Chief Statistician of the European Union from 2008 to 2016. He worked at the German Federal Statistical Office for 30 years, ultimately as its president. He was the first chair of the UN Committee of Experts on Environmental Economic Accounting, UNCEEA, from 2005 to 2008, and member of OECD's high-level expert group on the measurement of economics performance and social progress from 2013 to 2018. Since 2017, He has been a researcher at the Department of Statistical Science, Sapienza University of Rome, and the president of FENSTATS, the Federation of European National Statistical Societies. He wrote a book entitled Official Statistics 4.0, Verified Facts for People in the 21st Century. I recommend you to read these fascinating books to seize opportunities and know the challenge of official statistics in the 4.0 era. So today, Dr. Radermacher will present entitled Sociology of Measuring the State, Official Statistics 4.0. So please, Dr. Radermacher, the screen is yours.
Okay. I hope you can hear me now.
Yes, it's clear, Professor, yes.
Okay. Then I will share my slides. Okay, you can see my slide now?
Yes, clearly.
Okay, okay, fine. Then, let me see. Well, in comparison to the preceding paper and presentation, I think you have to change the way of looking at statistics, because I will present you more or less the complementary items and complementary questions around practical implementation of statistical methods in a paper which is called Sociology of Measuring the State. And so there is no mathematics in my presentation, but it is the rest of the statistical world which I will guide you through in my talk. And the first thing is that I am considering what statistical products, what statistical facts are. And in my view, it's quite important to understand that statistical facts, statistical information is produced. So it's a product like other industrial products, other handmade products, but it's produced, constructed, made. And at the same time, statistics need to be objective. So in this kind of conflict of two objectives, to be constructed and objective, the question is how we can achieve a good balance for the best possible statistical facts. And the way to achieve this is that we codify and verify what we mean when we say statistical quality. I will come back later to it. For the special case of official statistics or public statistics, it's important to bear in mind that there needs to be a social, a political mandate, which gives a kind of mission and a job to do to official statistics. And the second is a social license, which gives the tools, the capacities, the budget, and the legal fundament on which statistics is based. So I think this is more or less the world I am leading you through. And in addition to mathematical and statistical methodology, I am using three additional conceptual approaches or concepts or methodologies. First is for the management of a statistical factory or the construction of a public infrastructure. I use the total quality management as it was introduced firstly by W.E. Deming. For the sociological part, what is official statistics' role in the public discourse? I use the concept which in French is called économie des conventions, the convention theory as it was introduced by our French colleague Alain Droisière. And for the question of what is good statistical literacy or data literacy, I use a concept which was more recently introduced by my German colleague Katharina Schüller. I will come back to this as well. So, as to statistical quality, there is meanwhile a set of quality codes at the UN level. It's the fundamental principles of official statistics here, which were adopted in 2013. And at the European level, we have something quite similar, a bit more detailed, which is the European Statistics Code of Practice. And typically both apply statistics to three different strengths of three different aspects. The first is the output aspect. What is good quality of a statistical product? And this is not just accuracy, but it is comparability, timeliness, relevance, and so forth. The second is how have statistics been produced? Are the methods up to date? Are they the best possible? Do they follow international standards and so forth? Third is who is producing statistics? Is the institution independent? Does the institution have the appropriate capacities, skills? And I have added myself a fourth category, which makes a difference, namely for whom and for what do we produce? Because it makes a difference whether we produce statistics for the public discourse or just for ourselves, for our company, and so forth. Now comes a little bit a shift, because I think we need to consider what is going around in our societies. And yesterday, the COP26 in Glasgow, Scotland, was finished with some declarations as regards climate change and corresponding policies. So my perspective to the next years is coming from the definition of sustainable development. Sustainable development was introduced firstly already in 1972, so this is 50 years ago, almost, by the Club of Rome report, with a lot of statistics in it. Secondly, we have had the Brundtland report for the UN, Club of Rome in a new version, where the Brundtland report defined two concepts which come together, namely the concept of needs and the concept of limitation. And so we have to find a balance between equity within generations and equity between generations and between countries when we look at the global strategy of sustainable development. In the Rio conference 1992, there was firstly the link to statistics introduced, and it sounds quite modern when we read this almost 30 years old document. It says, in sustainable development, everyone is a user and provider of information. That includes data, information, packaged experience, and knowledge. And we need to bridge the gap between producers and consumers, and we need to improve information availability. So this is more or less the old mandate to statisticians, the statistical community, when it comes to sustainable development. More recently, presentation of sustainable development included this famous donut of Kate Raworth, and she has used this visualization in order to show that there is an inner ring, an inner circle, which is the needs of the human mankind in terms of water, energy, policy voice, and political voice, and so forth. And the outer circle is the limitations of nature. So sustainable development is a solution space within these two circles. When we look at countries around the globe, then we see that this green solution space here, word capacity, biocapacity as an upper limit, and the very high human development as a lower limit, then we see that none of the countries is currently fitting the criteria of sustainability. The rich countries in Northern America, Europe, and Japan, for example, they are wealthy, but their ecological footprint is too high. The poorer countries, here we have Indonesia, they would fit the ecological footprint, but their welfare is not high enough. So this is the situation. And against this situation, sustainable development was taken as an approach to the UN strategy towards 2030. And we have now 17 goals, 169 targets, partly quantitative, and remarkably high, a number of 231 defined indicators defined by the statistical community. And each year we see a kind of report from the UN, but also from each country, which tells us how far the indicators show progress or not. This is the current report of the European Union. And what you can see here is that in this arrow, you see the progress which is meant to be achieved. And here are the sustainable development goals which are making good progress. And here is the number of indicators and goals which are falling behind. So, for example, climate action is far away from being achieved according to the plan of the UN. Now, what does this mean for statistics? This is now the crucial question. And if you look at the European Union report, we see that in all the chapters, in all the goals, we have a mixed match of different statistical silos. So, for example, here, agricultural production is not any longer just agricultural production, but it includes also environmental data. The same for energy consumption, the same for economic growth. You see, for example, here that resource productivity has now become part of sustainable economic growth. It's not any longer just GDP. Quality of life, decoupling environmental impacts from economic growth. Of course, there is a lot of cross-cutting and so forth. So while we are currently fighting the pandemic, also in statistics, there is the big brother waiting at the border for the next round. And as we know that statistical programs and products are not easily to be changed, this takes a lot of time, we need to prepare now in order to not be surprised as we were with the pandemic. Lessons learned. Sustainable development, this is the future politically. It defines an integrated framework for politics. Previous political divisions and silos are to be absorbed into it. Diverse cross-references and references exist. So a great challenge for statistics. There is no longer a one-to-one relationship between a group of users and a silo of statistics. We need to change to open smart statistics, and I will tell you in a minute what this means. We have to integrate data from external sources, which are non-official, and we need therefore to use a new approach to quality assurance. We need to enhance networks and partnerships with other statistics producers, and the entire business architecture and business model needs to be changed. So what is also to be borne in mind is the situation of digitization and globalization around us. While we believe as statisticians that we are living in an era of let's say data gold rush, others see this as the death of truth. And There are a couple of reports which highlight the importance of understanding this dilemma between different strands of sociological developments. For example, this one of the Royal Statistical Society of the United Kingdom, which says our democracy relies on the quality and trustworthiness of data in the public domain. This is a report from an English journalist and researcher who said the statistical logic of the past 2 centuries is being replaced by a data logic, which is a danger. I will come back. And this is a report from the American Statistical Association, which puts the finger on the need to improve statistical education at all ranks. So in the last 30 years, we have been moving from a kind of first generation of evidence-based decision making in the 1990s, where decisions were augmented by evidence, to a situation now where decisions are automated by evidence and statistics, and this means a lot of burden on ethics and preparedness for statistics. There is a kind of unsharpness relation which was expressed by Charles Goodhart, an English economist. He said any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. So the more relevant you are, the higher is the risk that politicians will try to manipulate your data. And then lastly, we have this sentence of Michael Gove, and which has linked to the growing danger of anti-intellectualism. So finally, globalization makes a difference for national statistics, both in terms of environmental risks and economic value chains. For example, here, the Irish GDP moved in 2015 up by almost a quarter, because just one company moved their balance sheets from outside Europe to Ireland. Now, in summary, the world we live in is characterized by different trends, evolutions, and revolutions. Of course, we have the data revolutions, Internet of Things, artificial intelligence. This is the technical part. By the society, we have 4 different trends. We have a kind of mainstream in the technocratic elite, which is believing that evidence-based decision-making is the gold standard. And they are depending on evidence. Then we have a critical civil society, which is pro-evidence but not happy with what is produced currently, the GDP, for example. Then we have a kind of do-it-yourself statistics coming from the influence of data sciences, pro my own evidence, so a multiplicity of outcomes. And we have the contra-evidence of post-truth politics, the Donald Trumps of this world. Now, official statistics, in a strategic perspective, can look back to a history of almost 200 years. And we are now in this phase 4, where we have not only computers and a lot of data, but methodologies are being developed, which allow us to make use of new data sources with the corresponding problems that I am looking at. So the new more or less standard of official statistics is so-called trusted smart statistics, a systemic augmentation of official statistics. And this is more or less the general picture how this looks like. So in the middle, we have the statistical factory, statistical production. In the past, there was a kind of control of the process lines from survey data to statistical production to statistical products, or from administrative registers to statistical production to statistical products. Now, in the new world, we see that we have new digital data which can be used, sensors, smart devices, online platforms, and all of them, all of them go into this new machinery, a new factory, which has to be prepared to be able to assemble and quality check different source incomes, inputs from different data sources. So the design principles here are first to push computation out. Second, that we use multi-purpose data sources for multi-source statistics. So at both ends, the input and the output end, we have, let's say, not a one-to-one relationship. And we need a layered and modular organization of the data, not using standardized and a priori agreed methods. And the quality is not codified. Opposite to this is the strength of and weaknesses of standardized statistical analysis as we use it in official statistics, high comparability through standards, international, regional, time-wise, quality is codified and certified, which makes a huge difference. And on the other hand, the shortcomings are, of course, then that official statistics is less flexible, not tailor-made, and that it gives the producers a lot of expert power, which increases mistrust. So you see, it's not either or, but we have to find good ways to combine the two ways. But if we were only to look at individual statistical analysis as solutions to our current problems, we would jump not far enough. The new statistics factory would also like to include much more of, let's say, input from civil society. So there is something called citizen science, which explores combinations of, let's say, traditional science and including citizens and as co-producers of science. The same applies to the design of product and programs in official statistics. Here we can consider to much more what we have understood as teaching statistics is more or less this kind of mathematical clear methods only, but in practice statisticians had to do something like that. So our teaching statistics needs to include much more of the entire chain, the competences, the ethics, tailored to different groups of people, of citizens, and so forth. My last element is governance. The main objective is trust. So the public needs to trust in official statistics. So we need to have strong, independent, and innovative institutions which can give democracy a possibility to participate and let democracy control. And we need a consistency between national and international governance. My last slide is a summary. So the smart open statistics is the goal and guideline for business architecture in official statistics. The primacy of using existing data to be integrated data management. We need flexible offers for the use of data for the different user groups of official statistics. The public statistics need to be defined and organized as a kind of wider circle around official statistics, and a coordination by the chief statistician. Normally, it's the head of the National Statistical Office. We need a forward-looking program and product development like industry does. We need quality standards for public statistics going beyond the statistical office. We need to certify close cooperation between sciences and statistics production is absolutely crucial. For that, we need trust in institutionalized networks and partnerships. International cooperation, of course, is ever more important in the future. And last but not least, we need to improve data literacy, not only for experts, but also for the lay people, for pupil, for the man on the street and the woman on the street. So that's it from my side. Thank you very much.
Thank you very much for your presentation, Dr. Rademacher. I'm sure that the audience has more questions in their mind related to your presentation because, in fact, most of us here working in the same field of your topics. Very well, ladies and gentlemen, now we come to the question and answer session. Our team has summarized the questions from the link. We will try to have 2 rounds until 4 o'clock, and there is 1 question for each presenter per round. So the first question is for Professor Zhang Bernard. The question is, based on your experience, what kind of data that commonly erroneously mistaken with homogeneous slope, but in fact it should be treated heterogeneous? When that already happened, what are the worst consequences when we use this result? This question is come from Angela. So please, Professor Zhang Bernard, the time is yours.
Okay, thanks a lot for this question. So what is the main drawback? I think it's for forecasting. So you have several papers in the recent years who try to promote forecasting with panel data, and that's when you constrain the slopes to be identical, whereas they should not be identical, then that's where you're making the largest set of errors. So that would be my main point. Now I think that panel data, it's a game of combination. That is, because you put individuals at different periods and different individuals, you have a lot of room to disentangle different categories of individuals at different periods, and even more so if you consider more indices such as flows, if you have data related to flows from one country to another and so on. So that's you have a sort of an art of exploring how these slopes and marginal effect differs. So that would be my main topic. Else, as you've seen in the example, usually when we pull things which are very different, because what we obtain as slope is an average, it's something which has more common sense, and that's it. But it may not be all the best things you could extract from the data, where you have lots of room and possibilities to exploit, to make progress with those data.
Okay, thank you very much for the explanation, Professor. Now the next question is for Dr. Quarik. The first one is a statistic office collect data from many surveys and with the open source system in DevOps. Does it mean that the data can be freely utilized? And how does DevOps manage the data license and data security? This question comes from Maria. Please, Dr. Quarik, time is yours.
Sure. So actually, that's a good point. Official statistics can only be transparent up to a point, and the point is when individual data would be disclosed. So what I presented, that the process should be transparent. I was talking more about the code, the steps, the methods, but not, of course, the raw input data, because that would be either if you think about the census, for example, that would be every individual of a country with their characteristics. But there are approaches to generate, for example, synthetic data so that you actually can run through the process based on a synthetic data set and then see what happens in different process steps. That would be array around it. So you can see the process working, but then you would come to slightly different results because you don't have the original data.
Okay, thank you very much, Dr. Khawarit. For the next question is for Professor Wujuli. Regarding the forecasting model in your presentation, which one do you think gives better result on preventing new cases? The social distancing or banning the crowd? This question comes from Andika. So please, Professor Wujuli, the time is yours.
Yes. The question is which model gives better results on preventing new cases, social distancing, or banning the crowd. So if I understand the question correctly, the forecasting, my forecasting models, I mean the timeshare Ingachi model, they predict the number of new confirmed cases and severe cases. So it gives better results on it's not about the preventing new case, but it's about the just better prediction for the number of confirmed and severe cases in the next week. That's all. And then the next question is about why I use the Ingachi model when the data doesn't have a big volatility. Actually,
I'm sorry, Professor Wujuli, the second question is for the second round.
Oh, I see.
Yeah.
Okay.
So
Okay, sorry.
this is for each question. One presenter, one question. Thank you very much. Thank you very much. So the next one is for Dr. Radermacher. So with the global dynamization aggravated with the pandemic situation, what are the important key points for developing strong public official statistics? What should be changed first from the usual official statistics that we already implemented nowadays? This comes from Sari. So, Dr. Radermacher, the time is yours.
Okay, thank you very much. Yes, I think the first and most important point is the difference, as I try to explain, between strong public statistics and the traditional official statistics. If you look at traditional official statistics, then they focus normally very much on a set of statistics belonging to the socio-economic branch. But if we take now the pandemic, then we see that other statistical producers in the health sector come in, which do not yet belong to the system of official statistics with their codification. And I would like to recommend that this gap is closed so that we open the door and there is a strong cooperation and strong communication and organization which integrates former, let's say, standalone producers of statistics in the public sector into a wider system of public statistics. With services coming from the Statistical Institute, so I could imagine that the Statistical Institute gives a service which, for example, is advising in sampling, household sampling, so as to improve the data which come from households concerning the pandemic, so to be more representative and so forth. So there is a lot of possibility to improve when we open the door of official statistics and integrate in a coordinated way other public sector statistical producers and link them with scientists in the statistical branch.
Okay, really clear explanation from you, Dr. Radermacher, about the integrated process and to open the official statistic to fill the gap. So we can continue to the next round. Again, this question will be for Professor Jean Bernard. You have explained how we could do the trick of pulling and unpulling panel data econometrics. And in the case of we are handling a huge amount of time series cross-section data, or in recent days, there is a term of big data. Could we still apply the trick, or should we construct some kind of approximation? This question comes from Naufal. And please, to Professor Bernard, the time is yours.
Question. So the first is to the case where we have many individuals, and therefore, if we want to go to each individuals, that is to check the time series effect, it takes too much time. So that's with respect to the example I've taken, which was 20 countries around and 20 periods. So that's it. So in fact, what you could do is based on priors. That is, and that's actually what many of us are doing. That is, we expect that we have a group of fragile individuals, fragile firms, because they have too much debt or whatever. And then we split, based on our priors, the samples into categories to check and to identify different slopes at different events and so on. So that would be my answer, which is something not systematic, because if you have say, indeed you could run thousands of time series estimates, but also and you try to pull. So there are some technical ways to do something agnostic and then try to identify the groups that you could form. So that's an alternative possibility, which I guess is not quite developed, but there are definitely tools. That is, you test difference to a means of the slope, and you keep the group which is close to the mean, and you take the both of the side on the two of the extremes, and then you build this way already three groups and so on and so forth. But my answer is that indeed with many individuals, then you, with often short time dimension, then you would have to do this way. So that's my answer.
Okay, thank you very much, Professor. So it means that with the big data construct, the large number of individuals data with the shorter time periods. Yes. So yes.
No, yeah, I was meaning that we split the groups of the large number into large numbers subgroups, where based on our prior insights, that is, we expect that if there are lots of bets, they are different than the group with less debt and whatever. And then we would accept that these groups would have different behavior, and we test this.
Okay, Professor, thank you very much. So for the next question is for Dr. Kwarik again. So the one is awesome official statistics that you mentioned on sampling, such as calculating minimum sample, and can be modified by considering a local characteristics or maybe country characteristics. Question comes from Andrew.
Okay, so this list I mentioned, the awesome official statistics website or list on GitHub, it's not a tool, it's just a list of existing tools. So what you could use in different process steps. And yes, there are a couple of packages mentioned that are handling sampling. Two variations mainly for allocation. So think about certification or multi-stage sampling, you would have to allocate your sample. So that's something you can handle with, for example, sampling strata gives you that for certification, for certified sampling. And then you have at least one package I'm aware of that where you can actually like apply the sampling. So you just hand over the design you want and it samples. And there's also a package for things like area estimation, so that you tell them you have a proportion and you expect this sample size, what the error will be, can be calculated. So there are a number of packages on sampling, of course, because that's something really the core competency of NSIs, I would say, survey sampling.
Okay, thank you very much, Dr. Kwarik. So the next question will be for Professor Wujuli. Why are you using InGuards method when the data doesn't have peak volatility, and how you determine the model? This question is from Zaza. So Professor Wujuli, the time is yours.
Okay, thank you for the question. In fact, the InGuards model, InGuards method can be used for both big volatility case and small volatility case. I mean, because InGuards model employs the Poisson negative binomial assumption, so it can automatically reflect the size of volatility within the model. It's quite important to note the relationship between the mean and variance. If you think that for example, the Poisson assumption, Poisson distribution assumes that the variance should be equal to the mean. So if you think that the variance is much larger than the expected mean, then it's preferred to use a negative binomial model because it can incorporate the over. So in terms of determining the model, so as I showed in the slide, I used the proper score in null. So I mean, especially the length probability score. So it's the cross validation. By using cross validation, you can by comparing this the score value, then you can select the best one by minimizing the score function. It's quite simple one. Thank you.
Thank you very much, Professor Wujuli, for the explanation. I'm sure that your answer is really clear and can help the students. I think the one who asked your question is from the student from our campus, Statistical STIS. And for the next question is for Dr. Radermacher. The challenge of implementing smart open statistic and public statistic for developing countries such as Indonesia, does it need a different strategy than in Europe? This is because the infrastructure is not evenly distributed in an archipelagic country such as Indonesia, so that there are still development gap between the central and regional area, limited data management resources, ego sectoral problems between institutions, and so on and so forth. This question comes from Uni. So, Dr. the time is yours.
Yeah, thank you very much for the question. That's an interesting one. First, I would clarify a little bit, hopefully, that European countries are not that homogeneous as the question would suggest. Because if you take, for example, Luxembourg, a very small and very rich country, and you take Bulgaria, a large, very poor country, then you see that Europe does not, let's say, play at the same, absolutely the same level of welfare and technology. And even within countries, take Italy, for example, you have huge discrepancies between the north and the south. And you have also countries which have territories outside of, let's say, the continent Europe, France, the Netherlands, and so forth. But my answer to the question is that in principle, I would believe that the new approach of open smart statistics gives more flexibility to adapt to regional and country-wise situations. So the open smart statistics concept is the modern one, which also is easier to be transferred from, let's say, a homogeneous country like the Netherlands to a heterogeneous country like Indonesia. Because you can adapt your process to available data sources much more than you could do in a kind of straitjacket of traditional official statistics with hardwired processes and predetermined data sources. So you can use big data as they are available in your country and in your region. You can use geocoded data, take the population census, for example. I know from the Brazilian population census that they have heavily used pre-information from geocoded satellite images and so forth to improve the population census. And. So this open smart statistics gives more opportunity and more flexibility for countries like Indonesia, in my view, than the traditional, let's say, straight official statistics methodology and factory was.
Thank you, Dr. Radermacher. This is really interesting discussion, but unfortunately we have to wrap up to this point. And I'm really sorry that we have to finish before 4 because after this we have more upcoming event to closing ceremony of the ICDSOS 2021. Before that, please allow me to read my recap for the today's plenary session. To make a good forecast, the individual F-test of the homogeneity of slope coefficient is needed before forecasting the fixed effect model. The number of countries that could be pulled together for forecasting may be much smaller than expected. An upward testing algorithm may be run in order to pull homogeneous individuals in several different clusters. Else, the RMSA bias and the intercept bias are likely to be large for a large proportion of individuals. For the second presentation, the DevOps, development and operation in system development to a statistical production process. It provides benefits such as automate everything, testing, observing quality dimensions, fostering continuous improvement, and can be reproducible. Tools for many tasks in statistical offices are available as open source tools. Therefore, it provides room for improvement for many specific tasks of statistical production. And for the third presentation, related to the COVID-19 pandemic, forecasting for the new number of new confirmed cases and severe cases are also predicting the number of the new weekly confirmed cases in each district shows that an approximately 10 days lag exists between confirmed case and severe case, so that the government should be careful to ensure the adequate time to manage the increasing number of severe cases. Social distancing and ban on gatherings are different effect on the new current infection. Hence, non-pharmaceutical intervention should be continued after vaccination program. For the fourth presentation, the sustainable development provides great challenge for statistics, where open smart statistics comes into the stage with many data sources and multiple uses, integrated data management and flexible offers for the use of data. Official Statistic 4.0 requires us to learn, adapt, and change with the world dynamization, defining the public statistic coordinated by a chief statistician. Public statistics have to guarantee quality and certification. Therefore, it needs close cooperation between science and statistic production, access to data for promotion of networks, operation, data exchange, strict condition, use of international data source. So, ladies and gentlemen, finally, we come to the end of the talk. I would like to thank Professor Zhang Bernard Chatlang, Dr. Alexander Kwarik, Associate Professor Wujuli PhD, and Dr. Walter J. Dermacher for their informative and exciting discussion. And thanks to the audience for your active participation. Please give big applause for all of us. Hopefully, this discussion will be beneficial for everybody. I represent session of ICDSOS 2021 Day 2 would like to apologize to all of the speakers, audience, if some of you encounter any inconvenience during the event. Thank you very much for your attention and good afternoon. I return the floor to MC Nabila and Angga.
Gentlemen, we will shortly begin the documentation session. But before that, can we ask you to turn your camera on to be clearly seen on screen? For the documentation committee, please take screenshots.
And gentlemen, we have had a productive and inspiring time together. Unfortunately, this event is coming to an end. I hope you found the presentations at this conference informative and helpful. Now, we will now see awards for the best paper and the best presentation.
Second best paper, applied statistics. Article and Ekaria with the title Effects of Price, Income, and Household Characteristics on Ultra Processed Food Consumption in Jakarta, Indonesia.
The first best paper for applied statistics goes to Sultan Bustaman with the title Mobility COVID-19 Impact Quadrant Quantitative Approach to Analyze Community Responses to COVID-19 Pandemic.
Next, the best presenter for applied statistics. Erdina Ramadhanti with the title Digital Divide and a Social Investigation of Confidence in ICT Development across provinces in Indonesia.
Moving on for the science. The second best paper goes to Ika Nurwaili Fitriana and Muhammad Oli Fabri with the title Custom Analysis of COVID-19 Impact on Social Statistics. Goes to and Olivia Rizky Prasetyo with the title Adoption of Agriculture Mechanization on Paddy Farmers in Indonesia, Demographic Determinants and Access Influence of Adoption on the Yield.
And the last but best presenter of official statistics goes to Abdul and Hermanto with the title Financial Nutrition Impact on Poor Poverty during the Pandemic in East Java.
Congratulations for all of the awardees.
Ladies and gentlemen, to close the conference, I would like to now call upon Dr. Nasruddin, Head of Research and Community Studies Center, Statistica SDX, to present us with closing.
Statistician of the Statistic Indonesia Bapak Margoyono, facilitated by the Deputy for Methodology and Statistical Information, Bapak Imam Mahdi, Honorable Principal Secretary, Deputies, and Principal Inspectorate of Statistik Indonesia, the Honorable Distinguished Invited Speakers, the Honorable Director and Vice Director of Polytechnic Statistik ICDSOS, Chief of DP Province throughout Indonesia, representative of Korstat, Forum Perguruan Tinggi Statistika, and representative of ISI, Ikatan Statistisi Indonesia. Distinguished participants, ladies and gentlemen, first of all, I would like to thank the Almighty God for His mercy and blessing. We could hold the International Conference on Data Science and Official Statistics, ICDSOS 2021, through this virtual meeting. I believe that during these 2 days, all of us have obtained a fruitful discussion. This conference was maintained is strengthening the contribution of data science and official statistics to the society in the disruption era. We have learned and a lot of valuable knowledge for our distinguished speakers. On behalf of the ICDSOS 2021 Conference Committee, I would like to express our sincere gratitude for delivering interesting topics so that all of us can deepen our knowledge and understanding of the recent innovation in data science, applied statistics, and official statistics. We are also happy and congratulate the best paper and best presenter award. You have done your best to achieve such awards. I hope that all of us will continuously contribute to the advancement of data science and official statistics. The ICDSOS 2021 conference would not be conducted without the hard work, dedication, and valuable contribution of the committee, supporting decision and reviewers. We would like to express our sincere gratitude on the steering committee, the organizing committee, the scientific committee, who contribute tirelessly to make this conference plan efficient. We would like to acknowledge Polytechnic Statistik ICDSOS, Statistik Indonesia, Korstat, and ISI for providing all required resources and support to this conference. Our deep sense of appreciation also to the reviewer for their expertise, which ensure the scientific quality of accepted reports. Finally, I would like to thank all the committee members for organizing this conference and ensuring that it is conducted smoothly. I would also like to apologize for any inconvenience that you might experience during this conference. Ladies and gentlemen, there is a saying, ada perjumpaan, maka ada perpisahan. Which means, when there is a meeting, then there will be goodbye. However, in this ICDSOS 2021, I believe that it is not a goodbye. Instead, it is a see you again. Thank you for your participation in this conference, and we are looking forward to meeting you again at the next ICDSOS. See you again, and thank you very much.
Thank you, Dr. Nasruddin. And to end the day, I would like to be quoted by Seneca who once said, "Credibility comes from some
Let's all be guided by all the things we have learned throughout the conference and be able to see and influence our future. Most of us, as host today, would like to say goodbye and see you at the next International Conference on Data Science and Official Statistics. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.